Welcome to primary cable fault locating. When you're trying to locate a primary cable fault, you are working in a high voltage environment. Yes, it is important to restore the power outage, but it is more important that we follow our company's safety rules, even if they slow down our ability to locate the cable fault. As we describe how to make a fault locate, you may see some precautions that are not in your system. You may also see that we did not include some safety rules that you have in your system. Each utility has its own written safety policy, and it was written for everyone's protection, and this includes you. Regardless of what this video may indicate or tell you, or what any other person may tell you, follow your utility's safety rules to the letter. They have been developed because of the potential danger that exists, as well as past experience and problems in the field. When dealing with low voltage cables, it's easy to find the area where we'll be working. A house is without power, a street light is out, or some type of load fed from a transformer is without power. Identifying the area of a primary cable fault is more difficult because the high voltage primary cable can feed through a lot of transformers and cover a lot of distance from a substation to the terminal end of the cable run. Before making a primary fault locate, the first step is to determine the general area of the fault. Some of the methods used to define this general area are fault indicators, sectionalizing, a load management system, and above all, a good set of maps for your system. There are fault indicators for both overhead and underground, and there's a wide range of fault current trip levels available. You can obtain automatic reset or manual reset types. Since your system may vary a little from a sister utility, you should speak with a representative of one of the companies that produce fault indicators about the types you should use and where they should be installed. When fault indicators are properly used, they can speed up a primary fault locate process. Fault indicators are placed around each of the primary cables inside transformer enclosures, dip poles, and junction boxes. The fault indicator has a current trip rating that provides a flag indication when the current in the cable exceeds some preset value. If fault indicators are installed, you can move down the route of the primary run that's in trouble and check each transformer or position with an installed flag indicator. Each trip flag indicator that high fault currents have passed through the cable. When you arrive at the first enclosure where the indicator has not tripped, you can be sure that the fault lies between this position and the last enclosure where the fault indicator had tripped a flag. Current and complete system maps have a great deal of wasted time and energy when you are trying to locate the general vicinity of a primary cable fault. They should include detailed information about types of cables, cable lengths, and any other information which can help identify potential problems, such as number of times a given cable has failed and the position of where the failure occurred. Safety is the first primary priority on a primary cable fault locate. Primary cable fault locating is normally performed by what we call the thumper. And this is the high voltage capacitor discharge instrument, and it is dangerous. When you consider the danger that is present around any high voltage instrument and the danger of working with high voltage cables, there is no room for carelessness or shortcuts. Some of the absolute safety rules are the use of high voltage rubber gloves. These gloves shall be worn by everyone that will be working inside the transformer enclosure and during hookup, operating, and disconnecting of any high voltage test set. Approved live line tools shall be used for all shorting, grounding, and connections being made. Bare hand or body contact shall not be made to the test set or cable under test until the test set is de-energized and all parts of the circuit are grounded. The isolation of the test area must be complete enough to ensure nothing can enter the area except for the personnel who have been trained to work live cables. High voltage test equipment, barricades, signs, and operating personnel are some of the methods used to isolate the area. Now let's go over the methods and equipment for primary fault locating. The most common device used today is called a thumper. The thumper contains a large capacitor that is charged up to a high DC voltage by an internal power supply, and when the capacitor is at the desired voltage level that is set by the operator, it discharges its stored energy into the faulted cable. This high energy pulse travels the route of the cable to the fault. At the fault, an arc between the conductor and the neutral is formed with enough energy to ionize the air, creating a loud audible bang that can be compared to a large fireworks going off, like this. The bang normally occurs a few feet underground. It sounds like a thump when you listen for it above ground because the sound is muffled by the surrounding earth. Usually the thump sounds produced at the fault is loud enough to hear or feel with your foot without any special instruments. When this is not the case, an electrical acoustical pickup can be used. Besides the sound of the thump, we can also measure the amplitude of the large magnetic wave surrounding the thumper pulse as it travels the route of the cable. We do this with an instrument called ballistic impulse or magnetic wave detector. It is very important that thumper operators understand the difference between AC and DC grounding practices. Without proper training in this area, a safe fault load cannot be made. High energy pulses that come from a thumper can cause dangerous voltages to develop if solid low impedance ground connections are not used. Most manufacturers have invested many hours of R&D to develop a thumper circuit which offers the safest operation of their equipment. But all of this is of no avail if the operator defeats the purpose by not applying the proper hookup and grounding procedures. You could have more than one type of thumper in your system, and if you connect all of them up the same way without understanding their differences, you are certain to have a problem. On this simplified thumper circuit, note that the power supply and the capacitor are not directly grounded, and the high voltage ground and the thumper case ground are isolated from each other through a resistor called R. Depending on the brand and the size of the thumper, energy levels of 400 to 25,000 joules leave the capacitor and follow the conductor to the fault. At this point, the energy discharges into the shield of the cable and returns to the ground side or the high voltage return lead of the capacitor. The critical connection here is the high voltage return lead. It should be connected to the shield of the cable under test, S, to ensure the energy coming back has a clear and easy path of least resistance to the capacitor. The high voltage return lead should not be connected to the ground rod G or ground bus of the transformer pad. And whenever possible, the shield or concentric neutral should be disconnected or isolated from ground, C. If the thumper is being operated from a vehicle, a solid ground, B, must be applied between the vehicle and the thumper housing with a short number 2 or larger conductor to ensure the vehicle does not float or seek its own potential. This is also true for the earth ground of the vehicle. A driven ground rod, D, should be placed as close as possible to the vehicle to make sure the earth in the surrounding area does not float. If the thumper is set on the ground instead of in a vehicle mount, the same type of connection should be made. The thumper high voltage output and return lead should be connected to the conductor and concentric neutral, and the case of the thumper should have its own driven ground rod placed near the thumper with a number 2 or larger conductor. If your thumper does not have the resistor R, and some thumpers do not, a redundant ground should be made between the case of the thumper and the system ground. Always use a shotgun to install it, and make certain that the ground is not connected to the faulted cable neutral. Do not use a redundant ground if the thumper on thumpers that have the resistor are installed, or you will short the resistor out of the circuit, and this will defeat the purpose of the resistor. Before you connect the thumper to the faulted cable, learn as much about the fault as you can. After isolating the cable at both ends and grounding it for a short period of time, remove the grounds and make a resistance measurement to see what type of fault is present. The more you know about the fault, the easier it will be to make the fault locate. If the fault resistance exceeds 200 ohms, you will have to burn the fault down to 200 ohms or less before a low voltage radar set can be used. If the fault is a short, measuring a few ohms, the conductor is probably fused to the neutral, and again you may have to burn the fault open. The thumper will not be able to arc from the conductor to the neutral if they are shorted together, and without an arc, the thump or ionization of air cannot take place. The function of a burn is to condition the fault so that the best results can be obtained from the thumper or other test equipment being used. If a burner is not used, if a burner is used, the burn operation should be shut down every few minutes and the fault resistance measured again. Copper and aluminum are both good conductors of heat, and since the burn is nothing more than a sustained arc being established between the conductor and the neutral with lots of energy, the heat generated at the fault could conduct back up the conductor. This heat could damage the cable insulation over a large area. You can see what I mean in this demonstration. If the entire area of the insulation damage is not removed when the repair is made, you will have another fault very soon. Some people do not like to burn a fault unless they have to, because the heat generated during the burn could make the fault worse. If the conductor melts into a dead short contact with the neutral, you'll have a fault that's very hard to locate. To burn a dead short open can take a long time and do serious damage to a good portion of the cable near the fault. Some utilities prefer a DC high pot instead of an AC burn, and this will only use the burn as a last resort. In primary cable fault locating, the question of whether a thumper or any DC impulse testing hurts the cable is a hotly debated issue. And we have no decisive evidence that it does cause damage, but we do know that a thumper will not improve the cable. So care should be used to determine the voltage level before thumping. One other reason to keep the thumper voltage low is to make sure the thumper does not blow away carbon track or fragments of metal that are between the conductor and the neutral. If this happens, the fault resistance will increase and it will even take a higher voltage to once again establish a thump. A good rule of thumb is to thump at 1 or 2 kV over the amount of voltage needed to break down the fault. If you have a good electronic acoustic pickup of some type, you should be able to hear the thump even on low voltage thumps of 5 to 6 kV. One piece of test equipment you should have is a good radar scope of some type. It can be used to pre-locate the fault to a given area so you will not have to walk the entire route of the cable, listening for the thump. It will also reduce the amount of time your thumper is thumping the cable. In the past, low voltage radar was used to locate cable faults with some success. The major problem with the low voltage radar is that the impedance of the fault has to be 200 ohms or less. If the fault resistance is higher than 200 ohms, a burn operation must be made to condition the fault to a lower resistance value so a radar reflection can take place. This process can be very time-consuming, especially with oil paper insulated cables. In recent years, high voltage radar has proven itself to be a major time saver. The difference between a low voltage and a high voltage radar is the low voltage radar places the 50 to 100 volt pulse on the cable, and this low voltage pulse will not see a fault that measures over 200 ohms. The high voltage radar uses the thumper as its pulse transmitter, so a voltage pulse that is high enough to break down the fault can be used, and it only takes one pulse from the thumper. The high voltage radar uses a coupling device around the neutral of the cable under test. When the thumper pulse breaks over the fault, creating a thump, the energy coming back on the neutral starts the radar clock, so time measurements can be made. In this aspect, low voltage and high voltage radar sets are similar. They both time the reflected pulses being picked up and display these pulses on a screen. The operator can measure the distance between the pulses and can compute the distance to the fault. Once again, training is absolutely necessary for safe and effective use of the TDR. If you have questions, ask a qualified instructor who can train you or contact the company that sold you the equipment. They should be prepared to help you see and use the instrument properly. A ballistic impulse detector, also called a magnetic wave detector, is another valuable test system tool. When the thumper places a DC voltage pulse into the cable, the capacitor provides a high energy current pulse to produce this large magnetic wave that surrounds the voltage pulse. The ballistic impulse detector can pick up the magnetic wave traveling the route of the cable on its way to the fault. The way to hold the receiving antenna to see the pulse is different with each instrument, so read the instructions manual and learn as much about your instrument as you can. You should be holding the antenna over the root of the cable. Using the receiving antenna it's nothing more than a cable locator. The nulls and the peaks found by the way you hold the receiving antenna on the cable locator with respect to a cable route will also apply to how you hold your ballistic impulse detection instrument. Holding the antenna in the peak position may give you misleading readings when you're trying to find a magnetic wave fall off as an aid to finding the fault. The fall off you see may be because your antenna is not 90 degrees to the route of the cable. If you hold the antenna in the null position and stand just off to one side of the cable so you do not see the null, you might try using ballistic impulse detection as an aid to finding your fault. You can also use this method in a moving vehicle if the overall sensitivity of your instrument is high enough to pick up the magnetic wave that's that far away from your antenna. Ballistic impulse detection is of little use within 30 feet of the thumper. A large magnetic wave surrounds the thumper and the thumper cables going out to the cable under test. So you must move 30 feet or more down the route of the cable from the thumper to set up your ballistic impulse instrument. The magnetic wave surrounds the thumper pulse as it travels down the cable. Notice that where it breaks over at the fault, some of the energy will enter the cable's neutral and travel to the ground rod at the far end of the cable, but most of it will return on the neutral to the thumper. If the ballistic sensitivity is too high, a small amount of energy that travels past the fault to the far end of the cable can be picked up and the signal fall off at the fault will not be seen. Stand 2 or 3 feet off to one side of the cable and set your ballistic impulse sensitivity control to a level where you receive a very small meter reading when the thumper pulses. And the meter readings will be lost if you move out 5 to 6 feet away from the cable route. If your sensitivity control is set too high, the magnetic wave will flood your receiver and you will not see the fall off of signal when you walk by the fault. Walk the route of the cable while maintaining your 2 to 3 feet distance off to one side. Since energy will be reduced at the fault, a signal fall off will be seen by the ballistic impulse meter, a few feet past the fault in most cases. When you find the spot where the meter falls off, continue past the spot 30 or 40 feet to see if the signal level comes back to where it was before the fall off took place. If the signal does not come back, you should readjust your sensitivity control for a very small meter pulse while standing just off to one side of the cable 2 or 3 feet. As you walk back towards the thumper, watch your ballistic impulse meter. If you obtain a larger meter pulse at the spot where the fall off was found, you are ready to use the acoustical portion of your instrument to listen for the thump. Since the signal fall off will take place just past the fault should be very close to where you're standing and back towards the thumper. If the ballistic impulse meter returns to a normal setting at some point 30 to 40 feet past the spot where the meter reading fell off, that spot may not be the area of the fault. Junction box grounds, water pipes, and other metal objects around the cable can disturb the magnetic wave in a given area. A bad order neutral can also create this false reading. If the neutral is bad, the currents returning on the neutral will jump into the soil and dissipate. Since the current spread out over a wide area, the signal is weak in one small area where you're standing. This reduced signal in one small spot produces a signal fall off on your meter. Once the currents see the neutral that is intact again, they will return to the neutral and will provide an increased meter reading once again. The last item we want to talk about before we take you outside to make a primary fault locate is the electronic acoustics used to listen for those thumps that cannot be heard. To have an understanding of your acoustical pickup, we need to talk about what sound is. Sound is a mechanical energy in the form of pressure waves. You cannot see them, but you can see the effects of them. Sound waves leaving a sound source would be like the ripples of water leaving the spot where a rock was dropped. As the ripples move away in all directions, they get smaller and gradually they lose their energy. If a ripple strikes a solid object, the ripple reflects back in the opposite direction and leaves some of its energy in that solid object. When sound waves of a thump spread out in all directions, the energy hitting a sidewalk, asphalt, or some other hard surface reflects back into the ground, and this hard surface then vibrates like the skin on a drum. This vibration reproduces the sound of the thump, and what we hear is not actually the thump. It's the reproduction of the thump energy making the hard surface vibrate like that of a guitar string. The major vibration point should be where the sound waves hit, and vibration would get smaller as the sound waves travel sideways through the hard surface. Since the loudest sound should be at the spot closest to the thump, we should always be able to listen for the loudest sound and tell where the thump is taking place. Unfortunately, this is not always the case. Sound travels at different speeds and with greater ease or greater difficulty in different materials. This can have an effect on the efforts to make a fault locate. In open air, sound travels approximately 1,000 feet per second, or just over 700 miles an hour. In steel, sound travels about 16,000 feet per second, or 11,000 miles per hour. In general, sound travels faster and with less energy loss in hard materials than it does in less dense materials. If you placed one side of your head in water so one ear was underwater and one ear was in open air, a noise coming from a boat on a lake could be heard by both ears, but the ear underwater would hear the sound first and with greater amplitude. Compared to many other materials, air is a very poor conductor of sound waves. If you place an ear on a railroad track, you can hear a train coming from a mile away because steel is a very good conductor of sound. If you stand up, you will probably see the train coming before you hear it, and this is because air is such a poor conductor of sound. Soil with air pockets like sand, silt, or a fresh plowed field, snow, bark, dust, grass, or leaves can be a problem if you're not using the correct microphone to hear the sound. Sand is the best example of soil which makes it difficult to hear sound being reproduced by a thump from below ground. When the sound waves reach the surface, a lot of energy must be released into the air before you can hear it. The sand is not rigid or bonded together, so it cannot vibrate to reproduce any kind of a sound. Using a microphone designed for a hard surface application produces poor results on loose ground surface, or one that lacks the rigid bonding that makes it vibrate as one single unit. It hinders our ability to hear the thump. How well you can hear the thump above concrete or asphalt surface depends on a lot of things. Like the railroad track, concrete and asphalt are both rigid, concrete being the most rigid of the two. If the soil is in contact with the bottom side of a hard surface, it reproduces the sound with ease. If there's an air gap between the soil and the hard surface, the sound has to break through the soil with enough force that it can still hit the surface hard enough to make it vibrate. Because sound travels best along the path of least resistance, cables in a duct can be a problem. A duct is a much better conductor of sound than the surrounding earth, so the thump sound will travel down the duct and emerge at both ends. As a result, at one end of the duct you may hear the sound of the very loud, and yet the fault could be some distance away. Remember that sound waves travel out of the cable at the exact spot where the thump takes place. If the fault is on the bottom side of the cable, the sound waves have to reflect off the soil below the cable before they can travel back towards the ground surface. Since some of the energy will be lost when the sound wave strikes the soil below the cable and reflects back towards the surface, in this case, a thump will be harder to hear above ground than if the fault were on the bottom side of the cable instead of the top side. It would be even harder to hear, is so-called hard to hear if the cable were in soft soil, since soft soil won't reflect the sound as well as a more dense soil. Sometimes you may even hear the fault at a fire hydrant or a transformer enclosure. Also, if the sound hits a water pipe below ground, the steel pipe will vibrate like a guitar string and the sound will travel down the water pipe with ease. When the pipe changes directions to some vertical riser above ground, the vertical riser could sound like the thump is coming from it. On a submarine cable, it is very hard to tell where the loudest sound is coming from. Sound travels very fast in water and with almost no energy loss, so you can hear a thump at a very long distance if your microphone is underwater. To thumping submarine cables, microphones have to be waterproofed and used under the surface of the water. Since water is not bonded into a rigid surface, it will not vibrate and reproduce sounds. But the molecules of waters are tight enough that kinetic energy will move from one spot to another with very little energy loss. A lake that is covered by ice can be another hard place to make a locate. You can hear the thump from a long distance, but you cannot tell where the loudest sound is coming from. Since sound travels easily in water and with almost no energy loss, lots of energy hits the ice directly above the fault, and some energy hits the ice in other places as well. In most places there's a thin air void between the ice and the water, but there are a lot of places where the water is touching the ice. Compounding the problem, the ice is very rigid and could act like the skin on a big kettle drum. If all these problems sound like impossible situations, don't give up. I'm only trying to show you that we have problems out on the street. But if you'll use electronic acoustic equipment with skill instead of luck, you'll be able to solve them. Two types of microphones are available for use with electronic acoustic instruments. The ground contact microphone is used on a hard surface of some type. It does not work on soft surfaces because it requires some type of movement or vibration where the microphone pickup touches the ground. Background is probably the biggest problem with this type of microphone. The next time you use a ground contact microphone, place it on a hard surface and listen to all the background noises you can hear. Dogs, barking, cars, birds, and people talking or walking around. Lift the microphone several inches off the ground and you will lose all this background noise. As with the railroad track, the sound waves hitting this hard surface may be some distance from you and traveling sideways along the surface in contact with the microphone. If you're going to hear a thump, it must be a louder sound than the background noise, or you won't be able to distinguish it from the rest. Never set a ground contact microphone by a crack or in a sidewalk or at the edge of a pothole or the footing of a building. If the hard surface material is not in firm contact with the soil, it could vibrate and produce a loud sound, even though the thump is striking some other portion of the hard surface. The other type of microphone you can use is the earth contact microphone. Its design is based on the sound's conductivity in a sidewalk. If you could stab a sidewalk into the ground on edge, the sound waves moving through the soil would strike that portion of the sidewalk that's below ground. The sidewalk would then vibrate, and if a microphone was touching the sidewalk, you would be able to hear the thump. The earth contact microphone assembly is a microphone installed in a steel spike which is inserted into the ground. One of the first benefits you notice with an earth contact microphone is the reduced amount of audible background noise. This makes work in a noisy environment much easier. Since a soft material doesn't vibrate like a hard surface, sound waves hitting it they don't travel sideways through it, and noise produced by a short distance away is lost before it can reach the steel rod. I use the earth probe microphone in the dirt at the edge of a sidewalk, even if the cable is under the sidewalk. I can increase my acoustical sensitivity since I do not have the background noise to fight, and I can hear thumps much easier. To evaluate acoustical instruments purchase, the performance of the instrument is of course important, but you need to look at several other things as well. Look for ease of operation, waterproof microphones, and most of all, make sure the instrument will not hurt you. Some of the acoustics on the market do not limit the audio output to the headphones. Unlimited output could change your hearing.